Jai Hind all of you. I am Dr. Rahul Bansal from Ajay Kumar Garg Engineering College, Ghaziabad. So this one is the next video lecture for the electron devices KEC 301. So let us start. So in this video lecture we will be discussing about the electron and the hole concentration at the equilibrium state. Right. So in the previous video lecture we had discussed about the probability of the occupancy of the electron. Right. So this was like given in terms of the Fermi Dirac function, right? So we had like measure or we had compute the Fermi Dirac function for the N-type semiconductor, for the P-type semiconductor and for the intrinsic semiconductor. But in this video lecture we will be discussing about the carrier concentration. Okay, we will be able to find the value of the electron concentration and the hole concentration, right? So mathematically if we see in the conduction band, the concentration of the electron is mathematically given by, if I like consider this, that this N naught denotes the this N naught denotes the number of the electron, or you can say electron concentration at the equilibrium state, right? So N naught is given by integration where this E varies from EC to infinity. It means that we are considering, if I consider this as conduction band energy level and this as valence band energy level, then this limit is like lying above this energy level. So this energy level will be this belonging to this integration, and we are computing the number of electron, or you can say electron concentration in this region. Let me use the other different color pen for this. If I say it's like green color, so in this region we are computing the number of the electron, or you can say electron concentration. So it is mathematically given by N naught equal to integration when this E varies from EC to infinity, Fermi Dirac function multiplied by NE. Now here we introduce the new term, that is NE. What is NE? NE is basically the density of the states, right? It is measured in per centimeter cube, right? So NE is basically the density of the states, and this NE multiplied by DE is the density of the states in the energy range of DE, right? If I say like this N naught, here this naught represent the concentration is in the equilibrium state. Okay, so this N naught is for the electron concentration at the equilibrium state. So if I talk about the hole concentration at the equilibrium state, it will be given by P naught, right? So P naught will denote the hole concentration at the equilibrium state, right? Now next is, we had already discussed about the density of the states and equilibrium state, that is N naught and P naught, right? Now electron concentration in the energy range DE is the product of the density of the state and probability of occupancy of the Fe, right? Now it is actually the multiplication, right? Now total electron concentration will be the integral over the entire conduction band, right? So if we integrate all over the conduction band, that is from the EC to infinity, then we will get the electron concentration, right? So from the previous relation we have, density of the states is directly proportional to like E1 divided by 2, right, which means that Ne increases with the energy E, while this Fe decreases with the increase in energy. We had already discussed this thing in the previous video lecture, that is, Fermi-Dirac function decreases as the energy increases, right. So this was in accordance with this graph we had, if you remember this thing, right. So this was like Fe and this was E. This x-axis is actually E and this was Fe. So from here we had concluded that this energy, if you increase the energy, then the Fermi-Dirac function value is actually decreases, right. Now next is, okay, so next is product of Fe and Ne decreases rapidly above the conduction band energy level. Okay, so it means that a very few of the electron will be occupying the energy state above the conduction band, right. So it is like similar argument for the hole also, right, but the whole whole energy decreases as we move downward, right. Now this is the graphical representation, right. If I consider the intrinsic semiconductor, so basically intrinsic semiconductor Fermi energy level lie at the middle of this, right. So if I consider this as like conduction band energy level, this as valence band energy level, then this middle will show the Fermi energy level. We already discussed about this thing, right. Now density of the state will be like same for the intrinsic as well as for the extrinsic semiconductor, right. So it will be like this one, exponential term. Now if I consider the intrinsic semiconductor, we had already discussed about the Fermi-Dirac function also, right. So this one is the Fermi-Dirac function for the intrinsic semiconductor, right. So if you multiply these two, right, and integrate this, right, so what you will get is number of the electron, or you can see electron concentration and the hole concentration. So it is computed to be this one. This area shows the this concentration, actually electron concentration, and this gray shaded area shows the hole concentration, right. Now come to the extrinsic semiconductor. So first is one, so first one is n-type semiconductor. So n-type semiconductor consists of majority of the electrons and minority charge carriers are hole, right. So Fermi energy level will be just below the conduction band, right. So it is just below the conduction band. So this Fermi-Dirac function will be symmetrical about the Fermi energy level, as we have discussed in the previous video lecture, right. So as you can see, it will be like this one, it will be symmetrical about this Fermi energy level. And if we integrate, if I multiply this first graph with the second graph and integrate this, what I will get is number of the electron, you can say electron concentration, and this one is the hole concentration. So from this graphical representation also, what we can say? We can say that this is this electron concentration area is much larger than the hole concentration area, right. So next is p-type semiconductor. So in the p-type semiconductor, this Fermi energy level lies just about the valence band conduction, valence band energy level, right? So density of the state will be this one. It will be like constant for all the three, right? Now if I next is this Fermi Dirac function will be symmetrical about the Fermi energy level, right? So it will be like this one, and if I multiply this Fermi Dirac function with the density of the states and integrate, then what we will get? We will get the concentration of the electron and the holes. Now concentration of the electron for the p-type semiconductor is this one, right? And hole will be this one, right? This blue shaded region will show the electron concentration, and this gray shaded region will show the hole concentration, right? So what we can conclude? We can conclude that we can find out the value of electron at the and the hole concentration at the equilibrium for the n-type, p-type and intrinsic semiconductors, right, using this Fermi Dirac function. Now next is, if I want to represent all the electron distribution in the conduction band, and if I say like density, effective density of the state is like Nc, right, then N naught, which is the electron concentration at the equilibrium, it will be equal to Nc multiplied by Fermi Dirac function at that conduction energy level, which I am just talking about. So we have to make some assumptions also in this case, right? So EF, that is a Fermi energy level, lies at least several kT below the conduction band energy level. That is, EC minus EF is much greater than this kT value. If it is possible, then FEC can be simplified as, so FEC will be equal to 1 upon 1 plus EC minus EF divided by kT. We have replaced the E with the EC. That is, we are only talking about the energy level, which is above the conduction band energy level, right? Now, if this condition follows, then this equation can be rewritten as e raised to power minus of EC minus EF divided by kT. So this is the more simplified form of this one, right? Now next is, if I put this equation of FEC in this, if I say this equation is equation A, right, then I will get N naught, that is the electron concentration, is equal to Nc e raised to power minus EC minus EF divided by kT. Now, if you see carefully, N naught will increase, that is the electron concentration will increase as Fermi energy level moves closer to the conduction band energy level, or you can say EC minus EF, if it is decreasing, then N naught will increase. So this is the conclusion from this previous discussion, that is from this mathematical equation we can draw this conclusion, right? And this Nc value, that is the effective density of the states, is mathematically represented as, right, this Nc equal to twice of 2 pi kT Mn asterisk divided by h square whole raised to power 3 by 2. So if you see carefully, this Nc is a function of temperature, right? So next, we also conclude that electron concentration increases when the EF move closer to the conduction band, where this Mn asterisk, if you see carefully, this is actually the effective mass of the electron. We had discussed about the effective mass of the electron in the previous video lectures. What is effective mass of electron? Actually, rest mass of the electron is 9.11 into 10 to the minus 31 kg, but this is not the effective mass of the electron. It is something else, or what you can say, we can say that it is actually higher than that of the rest mass of the electron. Typical value is 1.08 into 10 to the minus 31 into 9.11 kg, right? So it is actually 1.08 times rest mass of the electron. So this is actually the effective mass of the electron. Now, in the same way, we can also find out the value of P naught, that is the Hole concentration at the equilibrium. It is given by NV, that is effective density of the states in the valence band, multiplied by 1 minus FeV, which is the Fermi Dirac function for the hole, right? So the probability of finding the empty state at the valence band energy level, okay, and if I assume that this EF minus EV is much greater than this KT, then 1 minus FeV can be like written as 1 minus 1 upon 1 plus e raised to power EV minus EF divided by KT, right? Now next is, it is actually equal to e raised to power, it can be written as, or it can be simplified as e raised to power minus of EF minus EV divided by KT, right? So we can find out the value of this P naught, which is equal to NV e raised to power minus EF minus EV divided by KT, right? And we can also draw one conclusion from this mathematical equation, that is, Hole concentration will increase as we move, as EF moves closer to EV. It means that EF minus EV will decrease. If at all EF minus EV is decreasing, then correspondingly P naught will increasing. P naught will increase, right? In this mathematical expression, this NV is equal to twice of 2 pi KT Mn MP asterisk divided by H square to power 3 by 2. This effective density of the states in the valence band is also a temperature dependent parameter, right? So NV is directly proportional to T raised to power 3 by 2. So this is actually the mathematical equation, right? So thank you all of you. So this is all for this video lecture. Thank you. Jai Hind.